I just wanted to give you guys a quick supplemental if you're a bit confused on the concepts that we taught on the Monday lesson. So to start off with, I'm going to be going over the Bohr model and what exactly an atom is, right? It's not a very straightforward process. Okay. So I'm going to start with the very center, right? The nucleus. So now there's two different types of particles in the nucleus. I'm just going to color one of them white, and then, or grayish, and then I'm going to color the other one the blue. Blue. Let's see. Okay. This one is what we call a neutron, and it's represented by just an N. And that is what we call a proton, which is represented with a B. Now, important thing to know about these two particles are their charges. On this particle, there's no charge at all. Neutron is neutral, right? Neutron, neutral. It's a pretty easy way. They named it pretty well, actually. And then the proton has a positive charge. So I'm just going to represent that with this positive charge on that proton. So that means proton positive, right? Proton positive, you can just remember the B. Proton positive. Now in an atom, you have both of these. Right? You'll have your protons over here, it's like bundled, and the kind of, subatomic glue, what I'll call it, is the neutron. It keeps everything together, it keeps the atom stable so that it doesn't break or fall apart. That's the kind of the job of neutron. So you have your protons, which are positively charged here, the blue, and your neutrons, which are neutral charge. Now, what charge is this entire thing then? I want you guys to think about that. Just pause for a second. What do you think the charge of this entire thing is called? And I'll name it. This is the nucleus. Feel free to pause, and then after you thought about it, come back. Okay. If you said it was positively charged as well, you'd be correct. The nucleus is a positively charged collection. Basically, the protons, which have a positive charge, and neutrons with no charge, they come together, right? And then what you end up with is still positive charge, right? Nothing's canceling it out. Now, I'm just going to quickly remove all of this. I'm just going to start anew. Now, there's one more particle I'd like to introduce you guys to. And that is my good friend, the electron. I'm actually quite well known in the electron community. Founding member. No, I'm kidding. But this is an electron right here. Now, electrons are special. While protons and neutrons are just chilling in the nucleus, an electron is surrounding it. I'll show you what that means later, but first you have to understand our good friend, the electron here. You represent it with an E negative. That E negative is important. And as you could probably tell with the negative sign here, this is negatively charged. So electrons are negative. You can just remember this was the process of elimination, right? POE, process of elimination. If you know that a neutron is neutral, right? Neutron, neutral. Oh, I'll draw this way. If a neutron is neutral, right? And then you have your proton, which is positive. I'm just going to abbreviate. Then the only other type of charge this could have is negative, So electron is negatively charged. Well, you might be wondering, okay, but if the electron isn't in the nucleus, then where is it? So I'm gonna actually show you guys the Bohr model to help you guys understand this first. There are many other models, but for this class, you will only really be going over the Bohr model and then occasionally the electron cloud. Right. Just for this video, I'm only going to be talking about the Bohr model. Now, in the Bohr model, you have a nucleus, right? You have these molecules here. Some of these are going to be protons, some of these are going to be neutrons. Right. Oh, an important exception to this is actually hydrogen, the very first element. Hydrogen has no neutrons. It has a thing called an isotope, which does, but hydrogen, most simple, right here. This is some random bigger atom, right? Bigger element. Hydrogen is actually quite special. So around it, kind of like orbiting it like a planet, you can find your electrons. Right? Fine. Or not electron, sorry, it's a singular electron. Now, it might be hard for you to like understand the trend with this, but I'm gonna go over it with this one. Now, I know I'm quite bad at drawing circles, but let's just say there's 5 here, 5 blue ones, let's say, 5 blue, right? 5 protons. Oh, we can keep this there. Right? I'll just box this in so you guys know I'm not talking about that. You have your 5 protons here. Now, we're going to draw the electron cloud. For this one, I'm going to try and keep it pretty close to scale. And what that means is I'm going to actually go a mile in this direction, this upward direction. Miles. I'm going to go for miles. In all of these directions, I'm going to put an electron. Right? Because to scale, the electrons are super far apart from the nucleus, right? The nucleus right here. Sorry, my handwriting is quite terrible. So you have your nucleus, right? I'll draw a little better, like a tiny dot. And then like very far away, very far, you'll have your electrons. Right? To kind of just tell you like how big the scale is. This in nucleus is super tiny. Right. Anyway, I'll just remove. Oh. For now, let's leave that. Okay. Now let's draw actually where these electrons are going to be. And as I said earlier, there's going to be a circle just going around the nucleus, just orbiting it. Kind of like planets. You're just going to have your electrons here. Just going to have an electron here, and you're going to have an electron here. And now, here's where things actually get a little bit interesting. Right. Or not interesting, I'd say it's not what you'd expect. So, there's an important rule to follow with these electrons. Because these electrons kind of don't want to be near each other. That's why they're opposites. You know, we're not buds. And the reason for this is actually exactly like with magnets. Right? With a magnet, you have your south side, and then you have your north side as well. I can draw that. Here, you have your north side as well. And then this is going to attract the opposing. This side's going to attract the north side. And this side is going to attract the south. Oh, it's a pretty bad shade of red. So there's a force here. And then there's a force. Oh, actually, I'll draw it the other way. There's a force going in this direction, trying to bring them together. All right, and that's magnetism. We learned that like elementary school, right? Pretty basic. But cool thing is, actually I'll leave it. Same thing applies to the electrons. Instead of north and south, we can just ignore that. And just like the charges I was talking about earlier, this becomes a negative, this becomes a positive, this becomes a negative, and that's a positive, right? So you have these negatively charged electrons, right? I'm just going to draw negative here, negatively charged. And what keeps them there is the positive charge from the nucleus, right? Because you have your protons there. So that's why they're orbiting there, right? You can think of it kind of like magnetism or gravitation, whichever one helps you kind of understand it. You have these electrons, which are attracted to the nucleus, so they're not just going to go flying off at the speed of light, right? But since they're both negatively charged, another thing about magnets that also applies is that same sides don't attract, right? Opposites attract, same repel. So these electrons are kind of going to want to stay away from each other, right? And since this first kind of like, I'd say like shell, let's call this your shell here. This first shell is actually quite small. So we only have 2 electrons there. So the first, I'm just going to write it here. First shell has 2 electrons. Okay, that's the notation for an electron. Now, when we go outward a little bit, these other shells, remember this isn't actually how big these are relative to each other. This is not to scale. Right? The second shell can actually hold way more. It can hold 8 electrons. So second shell has 8. And in fact, so does the third shell as well. It can hold 8 electrons in it. And this leads us to what's called the octet rule. Right? This shell can have 2 electrons in it, and that one can have 8. Right? Octet with 8, but it also applies to the first one too. Now, an important thing about making your Bohr model, right? This is your Bohr model, is understanding how many of each particle there are. So now I said there were 5 protons here. So now going back to our hydrogen, you have a little tiny hydrogen. You can see that there's 1 proton. That's a very terrible one. 1 proton and then 1 electron. So that 1-to-1 ratio, I'll just write it off here. 1-to-1 ratio of protons to electrons will always be true. So you'll have your protons in there, in this nucleus, right? You'll have 5 of them. So on the outside, in order to make this neutral, right, to cancel out the charges, you'll also have 5 electrons. Right? It's just the most stable. Right? If you think about it, having a positive charge means a bunch of things will also be attracted to you, right? Example would be, right? People tend to not go after other people's boyfriends or girlfriends because they're in a relationship, right? They're not missing anything. Same thing here, right? These electrons are going to try and match the protons, so it's a 1-to-1 ratio. So if you have here, you have your 3 electrons, right? The actual place that I drew them doesn't really matter, but what's important is the number. So 5 electrons to 5 protons, and they're orbiting around it. And it's also important that you have only 2 in this first one, and then after you hit 2, you have to be like, okay, now one's full. I'm gonna have to go to the next one, the next shell. Now, hope that helps with understanding the Bohr model.